This video is brought to you by mywayteaching.com.
Now let us see a few examples. So the first example is the density of water is 1000 kg per meter cube. The density of water vapor at 100 degrees Celsius and 1 atmospheric pressure is zero point 0.6 kg per meter cube. The volume of the molecule is multiplied by the total number and it gives what is called molecular volume to the total volume occupied by the water vapor under the above conditions of temperature and pressure. Okay, we should analyze this problem. They have given the density, so we should analyze this problem. Now let us see the solution for this. See, for a given mass of water molecules, the density is less if volume is large, isn't it? So, the volume of the vapor is given by 1000 by zero point 0.6. Okay, the density of water is 1000 kg per meter cube, isn't it? And zero point 0.6 kg per meter cube is the pressure. So, which gives the volume of the vapor is 6 into 10 raised to minus 4 times larger. If densities of bulk water and water molecules are same, then the fraction of molecular volume to the total volume in liquid state is 1. As volume in vapor state has increased, that the fractional volume is less by the same amount, that is 6 into 10 raised to minus 4. If it is same, then it's the total volume in the liquid state is 1. If the volume of the vapor state is increasing, then the fractional volume it decreases by the same amount, that is 6 into 10 raised to minus 4. Okay. Now, the second problem is estimate the volume of water molecule using the data which is given in example 1. Okay, we should consider all the data which is given in the first example. See, in the liquid phase, the molecules of water are quite closely packed. The density of water molecule may therefore be regarded as equal to the density of bulk water. So that is given by density of water is equal to, or density of water molecule is equal to density of bulk water. That is 1000 kg per meter cube. Okay. To estimate the volume of a water molecule, we need to know the mass of a single water molecule, isn't it? So we also know that 1 mole of water has a mass which is approximately equal to, yes, 1 mole of water has a mass which is approximately equal to 18 grams. If you convert it in terms of kg, it is 0.018 kg. Since 1 mole contains how many number of molecules? According to Avogadro's number, it contains 6 into 10 raised to 23 molecules. And the mass of a molecule of water is that is given by 1 mole of water mass by the number of molecules, that is Avogadro's number. We get mass of one molecule, that is 3 into 10 raised to minus 26 kg. This is the mass of one molecule. So therefore a rough estimate of the volume of a water molecule we can calculate as this is the mass of one molecule, and the density 1000 kg per meter cube. It gives 3 into 10 raised to minus 29 meter cube. In other words, we can write it as 4 by 3 into pi radius cube. So the radius is approximately how much? 2 into 10 raised to minus 10 meter, that is 2 angstrom. Okay. Now moving to the next problem. What is the average distance between atoms in water? So here we should use the data which is given in example 1 as well as in example 2. Okay. See, a given mass of water in vapor state has 1.67 into 10 raised to 3 times the volume of the same mass of water in liquid state that we studied. Okay. Okay, it is 1.67 into 10 raised to 3 times the volume of the same mass of water in liquid state. This is also the increase in the amount of volume which is available for each molecule of water. When volume increases by 10 raised to 3 times, the radius increases by volume when it is increases by 10 raised to 3 times, the radius increases by v raised to 1 by 3, or we can say 10 times. So 10 into 2 Armstrong, which gives 20 Armstrong. That is nothing but so the average distance we can calculate it as 2 into 20, that is 40 Armstrong. This is the average distance between atoms in water. Okay. Now the another one example. A vessel contains two non-reactive gases. Okay. One is neon, which is monoatomic, and oxygen, which is diatomic. The ratio of their partial pressures P1 is to P2 is 3 is to 2. So here we should estimate the ratio of number of molecules and mass density of neon and oxygen in the vessel. Atomic mass of neon is given by 20.2 mu and molecular mass of oxygen is given by 32.0 U. Okay. Now let us find the solution for this. See, partial pressure of a gas is in a mixture is the pressure it would have for the same volume and temperature if it alone occupied the vessel, isn't it? That is, the total pressure of a mixture of a non-reactive gases is the sum of partial pressure due to its constituent gases. This one we already studied, isn't it? So the total pressure in a mixture is equal to the sum of the partial pressures. Each gas obeys the gas law. Since V and T are common to two gases, we can write it as for the first one P1 into V is equal to mu1 RT, and for the second gas P2 into V is equal to mu2 into RT, isn't it? So if you divide it, we get P1 by P2 is equal to mu1 by mu2. So here 1 and 2 refer neon and oxygen. So here they have given the ratio, that is P1 by P2 is equal to 3 by 2, isn't it? So if you substitute in this particular equation, we get mu1 by mu2 is equal to 3 by 2, isn't it? So now moving to the first part of the question. So they have asked us to find the ratio of number of molecules, isn't it? See, by definition, mu1 is equal to n1 by na and mu2 is equal to n2 by na. We studied these formulas where n1 and n2 are the number of molecules of neon and oxygen, and Na is the Avogadro's number, isn't it? So if you take mu1 by mu2 is equal to n1 by na into na by n2, that is equal to n1 by n2, that is equal to 3 by 2, because we already know it, isn't it? So this is the ratio of number of molecules of neon and oxygen. Now coming to the second part of the question, that is mass density, the ratio of mass density of neon and oxygen in the vessel. See, we can also write this mu1 as m1 by m1 and mu2 as m2 by m2, where m1 and m2 are the masses of 1 and 2. Okay, and this capital M1 and M2 are their molecular masses, isn't it? So here both M1, M1, M2, M2 should be expressed in same units. If rho 1 and rho 2 are the mass densities of 1 and 2, then we can write rho 1 by rho 2 as M1 by V by M2 by V. That is M1 by M2 is equal to mu1 by mu2 by M1 by M2, isn't it? So we know mu1 by mu2, 3 by 2. They have given their molecular masses, that is 20.2, 32.0. It gives the value as 0.947. Okay.